Welcome back, Chem 20s. This is part 2 of intermolecular forces. We've looked at London dispersion forces already. Now we're going to jump into the second type of intermolecular forces, which would be dipole-dipole interactions. Now, dipole-dipole is an interaction between oppositely charged polar molecules. Now, this is dependent on being a polar molecule. So this is that asymmetry we talked about in that last video. There has to be a dipole, and the substance has to be, when you add the dipoles together, a polar molecule. Strength is going to be dependent upon the polarity of the molecule. So if we take a look, and we're going to look at the same example again as we did in the polar video, we're going to look at HCl. Remember, when you look up the electronegativity values of these in your data booklet, hydrogen is 2.2, chlorine is 3.2. Okay, now that means that chlorine is pulling. It has an affinity for more of the mass of this compound. And you've seen me with this before. Chlorine is pulling harder than the hydrogen on this shared bond. They're sharing it, but they're not sharing it evenly. So what happens is, because chlorine is more electronegative than hydrogen, chlorine actually has this slightly negative moment over here, dipole moment, where the hydrogen has a slightly positive dipole moment. And what we did was, if you remember from the last video, is we always draw a dipole arrow pointing to the side that is larger with electronegativity. And so we have this dipole arrow here. And so this side is more negative than this side. Therefore, we have a dipole that doesn't cancel out. This is polar. Therefore, HCl has a dipole-dipole intermolecular force. Now, because we're talking intermolecular forces, this is the forces between molecules. So I'm putting more than one HCl on here. I've got one HCl, I've got another HCl, and you can see where I have a positive end of this HCl's dipole is attracted to the negative end of this other HCl dipole. That means there's a force here. Now, this attraction is stronger than the attraction in a London dispersion force. And so this little dipole we've created between the molecules, this is the dipole-dipole force that we're talking about. It's stronger than London dispersion forces, but it's still fairly weak. We're going to be figuring this out based on, again, electronegativity values, because the substance has to be polar. Now, the third and final type of intermolecular forces, this one's the tough one. And if it was me, along with copying the notes, I would go in my textbook and I would read page 111 many, many times. I would read it first, I would watch this, I'd go back, read it again, especially the 2 bullet points to make sure you understand what hydrogen bonding is. Now, a lot of text is going to come to you really quickly right here. So I don't know where to put me. I'm just going to shove me down there. Okay, so hydrogen bonding, first of all, isn't actually a bond. This is one of those special dipole-dipole interactions. Think of this as very strong dipole interactions. Okay, this is when we have this simultaneous attraction between a hydrogen bonding, you need the hydrogen atom, and something else with an extremely large electronegativity value on the other atom. Now, the 3 that always has hydrogen bonding is when hydrogen is bonded to fluorine, hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen. The easiest way to remember this is the same thing you're thinking. We're probably on the same wavelength. When you think of chemistry, you think chemistry is really fun. So hydrogen bonding is really fun as well. Every time hydrogen's bonded to fluorine, hydrogen's bonding to oxygen, hydrogen's bonded to nitrogen, there is going to be hydrogen bonding. Now, this is key because of a number of points. One, you have a hydrogen that's bonded to something extremely strongly electronegative, which means they're not sharing very evenly. That fluorine or oxygen or nitrogen, it's getting most of that electron sharing mass there, which means this little hydrogen, he's going to be left unprotected. He doesn't have much of those electrons around him anymore. They're still there, but they're over on the fluorine side. So he's being left very, very unprotected. And what we say is he's unshielded. Think of this like a force field. So I have an example here of 3 ammonium atoms or molecules. And so let's look at 1 ammonium molecule when we look at this. So nitrogen has a very strong electronegativity value, 3. Hydrogen, quite low. So this shared area of electrons, more of the mass, significantly much of the mass is over here next to the nitrogen in all 3 times, which in turn means that these guys aren't going to share it very well. Hydrogens are going to be slightly positive. The nitrogens are going to be slightly negative. Well, this is going to leave my hydrogens as unshielded. The reason this is so important is that means when another ammonia molecule is around, this negative electrons of this nitrogen will be able to get in closer than they normally should be able to that hydrogen, right? Because if you think about it, the hydrogen's electrons are pulled close to this nitrogen, which means he's not repelling anybody. So this negative charge on this ammonium ion, this can come in here and he can get closer than normal, kind of snuggle in there and get a tighter force of attraction. That is called a hydrogen bond. So he's getting unshielded. This guy's moving in closer than normal. That allows these guys to have a much stronger bond than normal. And that is what we call a hydrogen bond. This works in ammonium. This works in HF, hydrogen fluoride. This works in water. Water has hydrogen bonds as well. Well, we've now looked at the 3 types. And to remind us, we went from weakest to strongest. London dispersion forces or van der Waals forces, they were the weak guys. Everybody had them. But again, we could rank them. The people who had the least had the smallest number of electrons. The compounds with the largest number of electrons, it had more London dispersion forces than the smaller number of electrons. If there was a tie, like in isomers, then we looked at stackability, right? The better it could stack, the stronger the London dispersion forces. Then we moved on to dipole-dipole. To have a dipole-dipole intermolecular force, you had to be polar. That was key. And then the strongest type of dipole-dipole intermolecular forces were called hydrogen bonding, and they were the strongest. You cannot have hydrogen bonding if you're not polar. If you're not dipole-dipole, you do not have hydrogen bonding. Now, I like to think of this as a continuum. If we look at electronegativity values, because some of us are very math-based, when you take the difference between these things, right? Br, they both have the same electronegativity value. They cancel out. They'd have an electronegativity difference of 0. This is where they fall on this table. These would be non-polar, covalent. There's no dipole arrow. Things like HCl, the example we keep talking about, it would fall here, 2.2, 3.2 difference of, no, 2.2, I don't remember what chlorine is. I'm going to peek. 2.2 and 3.2, it's a difference of 1. It would fall right in the middle here. This would be our polar covalent bond. And then way up here that we're going to talk about eventually, this is where we're going to look at ionic bonds and crystal lattices. And they have an electronegativity difference much greater than 1.7. Hope this has cleared up all of our problems. Please rewatch the video as many times as you need.